Hey, let's start our second lecture on selectivity and specificity. Selectivity we have done. We are done. We in this video we shall be talking about stereospecific reactions. Before we start, let me ask you a few questions to make sure that you have not forgotten. Ready? We have in the just previous video talked about what are regioselective reactions and what are stereoselective reactions. Now I'm giving you one example. You have to tell me belongs to which category. This is elimination, dehydrobromination. I told you, I sounded you, it's an E2 mechanism. So you get two products. One internal alkene, more substituted alkene and less substituted alkene. These are the two products. Tell me, what kind of reaction is this? Is it regioselective or stereoselective? Now, let me ask you another question. I'm not writing deliberately the other product, that is other structural isomer butene. I am writing butene. This is trans butene and this is cis butene. Now, what is the fundamental difference between these two reactions in terms of selectivity, whether you coin the term regio or stereo? In this case, tell me what? Undoubtedly, it is regio because the two are regioisomers or structural isomers or constitutional isomers. So this is regioselective reaction. The question of stereoselectivity does not arise because these are not stereoisomers. These are structural isomers. Doesn't matter whether the reactant is a stereoisomer or not, doesn't matter. Here it is not a stereoisomer. Had we taken a different group, say for example 2-bromobutane is for example like this, it is a case of optical isomer is a chiral center. Here could have been a chiral center, doesn't matter. We are looking to the products. These are two structural isomers, so it is regioselective, and this is undoubtedly major and this is minor according to Sajef rule, and you must be knowing the reason behind it. Now, in this case, undoubtedly your answer would be this is stereoselective. Yes, yes. Why? Because these are not structural isomers, these are stereoisomers. And this is major, you know, trans is more stable and this is minor. They are formed in unequal quantities, so it is stereoselective. Now let's see what is the difference between stereoselective and stereospecific. I'm giving you another example. You may be tempted to answer it is stereospecific, but it is not. Just hold on. I'll give you one more Example, supposing you are taking but 2 wine and you are hydrogenating it in presence of Lindlar's catalyst, that is palladized barium sulfate with a catalytic poison. You are getting nearly 100% cis but 2 It has a stereochemistry. It has a stereo identity. And if you are using another reducing agent, sodium liquid ammonia, you are getting trans. So can you call this nearly 100%? Nearly. But can you call it stereospecific? Because it is highly stereoselective. Almost completely in favor of this cis, not trans. Even then, strictly, you cannot coin the term stereospecific because there is no stereo identity of the reactant. For stereospecific reaction, there must be a stereo identity of the reactant. No stereo identity. And had there been stereo identity, if one stereoisomer is giving this, the other stereoisomer of this reactant would have given trans. This is unique, product is unique, and its diastereoisomer is unique, and its diastereoisomer is unique. So in that case, let us define what is stereospecific reaction. Stereospecific reaction is like this: a particular stereoisomeric reactant. For the first time, we are stipulating something on the reactant. Gives a particular stereoisomeric product. Both the reactant and product have fixed stereo identity. SN2 reaction with inversion of configuration is an example of stereospecific reaction. We'll talk about that soon. Similarly, bromination of alkenes, chlorination or bromination, that is the addition of chlorine or bromine to alkenes is stereospecific, anti-addition. Addition of hypohalous acid, HOCl, HOBr to unsymmetrical alkenes is anti-stereospecific. It is also regioselective for unsymmetrical alkenes. I'll talk about that very soon. So we are now not discussing at all about regioselectivity. We have done it. We are talking about stereospecific reaction. A fixed stereoisomer reactant, stereoisomeric reactant will give a fixed stereoisomeric product. Let us take an example. There are so many examples. Hydroboration-oxidation of alkenes is stereospecific. It is syn or cis stereospecific. Catalytic hydrogenation of alkenes is syn stereospecific. E2 elimination of alkyl halide is stereospecific. That is anti-periplanar transition state. I told you the E2 elimination earlier is stereoselective because it is giving both cis but2 and trans but2 in unequal quantities. I am not talking here the same. You just hold on. Here I'll be telling you which E2 reaction will be stereospecific. It's not all stereospecific reactions. There are some stereospecific reactions which there are some elimination E2 reactions which are stereospecific. Particularly the major product. I am talking of the major product. If it can have a minor product, we don't bother about the minor product. So in that case, we will say it is regioselective but stereospecific. Just hold on. Keep your breath intact. Epoxidation by metachloroperoxybenzoic acid to alkenes, not the bicyclic compounds or other compounds. Alkenes is stereospecific. Addition of carbenes, addition of singlet carbenes, addition of singlet carbenes to alkenes. Addition of singlet carbenes to alkenes to produce cycloalkane compounds, derivatives. So many other reactions, the organic domain is replete with several thousands of stereospecific reaction. This is an introductory program just to acquaint you what are those reactions. See, SN2. I talked about SN1, which passes through a carbocation intermediate. This is SN2. There is no carbocation. This takes place in one step. The attack of the nucleophile takes place from the opposite side, from the back side or from the rear side of the leaving group, and it passes through a transition state and not an intermediate, and it flips to the other configuration. This is called inversion of configuration. If this is R reactant, the product is S. If his reactant is S, the product is R. There is always a 100% inversion of configuration if it is strictly SN2. So in that case, it is stereospecific. A particular reactant R is giving S product. And the other stereoisomer, its enantiomer, is giving its enantiomer. The reactants are enantiomers, the products are enantiomers. Product is different from reactant, but the reactants in the two cases, two reactions are enantiomers. The products in the two cases are also enantiomers. They can be also diastereoisomers. In other examples, we shall find there can be also diastereoisomers. This is a concrete example. This is a 2-iodobutane, ethyl, methyl, hydrogen and iodine, and we are using NaOH, SN2 condition, acetone medium. SN2 is 100%. In that case, OH comes to the opposite side and this flips, inverts like an umbrella going to the opposite direction. So if this is R, this is S. And if you take S iodo compound, you get R alcohol. The product is alcohol, the reactants are iodide. So this is completely stereospecific. Always takes place via inversion if it is SN2. But if it's SN1, then it will be non-stereoselective, non-stereospecific, 50-50. Non-stereospecific because either R reactant will give you RS mixture, S reactant also will give you RS mixture. So the reactants might be different, but the product is same and 50-50. So you cannot coin the term stereospecific, nor you can coin the term stereoselective. E to elimination. I was talking about specific case where there is a dibromo compound. This is a vicinal dibromide, 2,3-dibromo butane, and we have taken the inactive mesoform. Here there is a center of symmetry, and we can rotate the single bond and can visualize a plane of symmetry, right? Now this, when you take meso compound, you are getting transbutene, because at the transition state, when elimination takes place, the two leaving groups should remain opposite to each other. This condition is called anti-periplanarity. Transition state. So therefore, the fixed reactant meso compound gives the fixed product E-butene. But if you take its diastereoisomer, any one of the active, if this is RS, supposing this is SS, or you can take RR, its diastereoisomer, you get cis product. If this is trans product, this is cis product. E-butene, Z-butene. These two are diastereoisomers, meso and active. These two are diastereoisomers. So this is a perfect example of stereospecific reaction. Now you may argue, can there be elimination of HBr to form a double bond here and double bond here? No. In the condition of zinc and ethanol, it is dehalogenation, not dehydrohalogenation, that is prevalent. So we are not considering at all dehydrohalogenation. If at all there is some product, 1%, 2%, We are not considering that. We are considering what is the alkene product, that is but-2-ene product. That in one case E, in the other case Z. Right? Now I am giving you another example of E2. This is another 2-bromo-3-methyl pentane. This is a chiral center, this is a chiral center, which are not identical type. So this is what we call trio type. Forget about trio, erythro. If you are not familiar, then you don't poke your nose on that. Simply the configuration here, according to nomenclature, this is 1, 2. 2 is R and 3 is S. I have already found out. So you just take it from me. And when you carry out dehydrohalogenation, in this case dehydrohalogenation, H and Br will remain anti during the elimination in the transition state, so that the final product is Z3-methyl pent-2-ene. But if you take its other diastereoisomer, this is 2R3S, this is 2S3S. The S3 is common, same, but the configuration at carbon number 2 is opposite. So these are diastereoisomers. So if this belongs to the trio community, either trio, say RR or SS, and this is erythro, RS or SR, whatever. This is RS, I'm sorry, this is RS. You could have also taken SR. The result would have been same. But its diastereoisomer, this is 2S3S, is giving E product. This is Z product, this is E product. The same requirement, anti-periplanarity. The two leaving groups should remain opposite to each other. And then you will freeze the molecule, put a double bond, you will find the product has a particular stereo identity. So a fixed stereoisomeric reactant gives a fixed stereoisomeric product. That is a stereospecific reaction according to the accepted definition. Now I'll give you a few examples and then wind up. Addition of bromine and chlorine to alkenes. This is E-but-2-ene, and the addition is anti-addition. So if I have written here little in a deceptive manner, but when the two bromine will descend in the opposite side, the addition mechanism is anti, this bond will be single bond. In that case, all the identical pairs will remain opposite to each other, so that it is meso. So I have rotated and brought the identical pair to the same side, that is the eclipse conformation. Forget about that, we get the mesoform. But if you take Z-but-2-ene instead of E, you get a DL pair, a racemic mixture. Because if this mode will give you 50% of one enantiomer, the other one, bromine, this bromine below and this bromine up, that will give you another 50%, not exactly identical, but it's mirror image. So the result is 50-50. But don't ask me, so since it is 50-50, you cannot call it a stereospecific. This is 50-50, it is a racemic mixture. This has a fixed identity. Nothing to do with meso. Meso and any one of these, they are diastereoisomer. So in this case, the mixture, DL mixture, RR and SS, the DL mixture is a fixed identity. So the Z-but-2-ene giving the racemic mixture, while the E-but-2-ene gives a meso compound. These two are diastereoisomers and they are fixed. So in this case, you have to take the DL mixture, the racemic mixture, as a unique product, not as a two different product. So these two are diastereoisomers, and these two, I mean any one of this and this, they are also diastereoisomers. So this is stereospecific. And the addition mechanism is anti. Just like in elimination, the two leaving groups were anti. In addition, the two groups added to the double bond should approach anti with respect to each other. Now the mechanism, let us not bother much about how it happens. It happens by a three-membered cyclic bromonium-ion intermediate. If you have studied the mechanism of addition of bromine or chlorine, you must have known free carbocation is not formed. It is a cyclic bromonium-ion intermediate which is formed, which blocks one side, the other side is to be attacked. So if bromide ion attacks this side, then bromine is standing up, this bromine is stooping down, and if this bromide attacks at this position, then this bromine stands up here. So this is one possibility. The other possibility is this, and these two are fortunately not identical. They are enantiomers, a DL pair, or it can be meso. If it is certain like the Z, if it is E, then it will be meso. These two are identical, is equal to, plus sign will be replaced by is equal to sign, and if this is Z, then it will be DL pair, the plus sign will remain, it will be a racemic mixture. So let's not talk about mechanism. It's my purpose was not to talk about mechanism more, because we will be producing videos on pure mechanism of each particular reaction, which is of significance to your level. Similarly, addition of an alkene, cis or trans, to a singlet carbene. If you have no idea about carbenes, then you have to wait. I have not yet produced videos on carbenes, but you can study from any source, right? So carbene is an electron sextate unstable species, intermediate, which is a divalent carbon sextate. So this is bromoform. In presence of a strong base, you find CBr2 dot dot dibromocarbene. So dibromocarbene joins here. The cis compound remains as cis cyclopropane. The trans will remain as trans. The stereo identity is retained, but the products are different from the reactant. This is open compound, open chain compound. This is a cyclic compound. This is an acyclic compound. This is alkane. This is cycloalkane. But the stereo identity is maintained. Cis gives cis, trans gives trans. Similarly, you have, supposing you have diazomethane and ether, just in presence of light, a nitrogen molecule goes away, and this carbene CS2 dot dot that attacks to form a cyclopropane ring. If you take cis butane, you get cis dimethyl cyclopropane. If you take trans, you get trans. So the addition of a carbene, a singlet carbene. I am talking of singlet carbene, and there can be a possibility of triplet carbene, which is not stereospecific, because you get a mixture of the cis and trans cyclopropane. Whether you take a pure cis butene or trans butene, if you are allowing the singlet carbene change into a triplet carbene by fanning out energy, that happens in presence of a large quantity of inert gas, say nitrogen gas in the gaseous phase. But I am not talking of that. You are taking ether in a liquid medium, you are carrying out the reaction. So there is no fanning out of energy converting the singlet carbene to triplet carbene. Forget about that. Then addition of hydrogen to alkenes. Supposing you have a Z alkene here, there are two different groups, so that hydrogen is another different group will join, and the addition mechanism is syn or cis, either both from the top or both from the bottom. So if the groups are all identical and they are remaining on the same side, then Z compound will give meso product, and the E compound will give you a DL pair. If this will give you D, this will give you its mirror image L. So to wind up, I gave you a few examples of stereospecific reaction. There are many more. I will be doing shortly a video on Diels-Alder reaction, which is both regiospecific and stereospecific. Regiospecific and stereospecific, I will tell you that. But once I introduced this aspect of specificity and selectivity. Specificity, particularly stereospecificity, is a very critical term. You cannot loosely use it. When both reactant and product, they have stereo identity and unique, in that case you can use stereo specific. Otherwise, better call stereo selective. But never ever call these examples I have given you as stereo selective. It will be suicidal. So far as this instructor goes, I will never accept to call them stereo selective, because there is a correlation between the reactant and product, stereo identity between the reactant and product. With this, I conclude this session. To wind up, do not be surprised when you see the term stereo-selective reaction used by an author or any instructor for all these above, discussed stereo-specific reactions. I have seen in many literature also they have written stereo-selective. They are using very loosely. This is stereo-specific according to definition. In fact, the term stereo-specific is sometimes loosely used, particularly in this case. If at all someone uses for these reactions in this video, say stereo-selective, undoubtedly not acceptable. Summary: stereoselectivity looks only to the different stereoisomeric products with unequal amounts, that is selectivity. The reactant may or may not have any stereo identity. Stereospecificity always looks at the stereo identity of both reactant and products. Different reactants produce different products with fixed stereo identity. So all stereospecific reactions can be called stereoselective, maybe highly stereoselective, but the vice versa is not correct. But not all stereoselective, maybe highly, maybe nearly 100%, cannot be called a true stereospecific reaction if there is no correlation between the reactant stereochemistry, stereo identity, and the product stereo identity. You can't call them in the true sense. But all stereospecific reaction can be called stereoselective, highly stereoselective you can call them with little, crude way. It's not a good way, but a crude way you can call them. But not all stereoselective reactions can be called stereospecific. When I say selective, I mean highly stereoselective. Right? So I'm giving you these three self-assessment questions to tell me. So when you add Hi to such a simple alkene, we find only exclusive product is this tertiary pentyl iodide, where there can be other possibility. There could have been iodide would have been joined here and hydrogen would have joined here, but this possibility doesn't take place. There was a possibility, so I call it a regiospecific. There are no two terms, two reactants, only one reactant, but this is a polar addendum. There can be two possibilities, but the other one is not happening. In that case, I use the term regiospecific. There is nothing to do with stereochemistry. Had there been two products, I here maybe 5% or 2% the other product, then I would have used the term regioselective. And what about this? This is paint to wine, added with water in presence of mercuric salt in acetic medium, give a mixture of 50-50 mixture of pentan-2-one and pentan-3-one. So in this case, what brand, what name you will give out of the three? Regioselective, out of four, regioselective, regiospecific, stereoselective, stereospecific. Undoubtedly, these are structural isomers. So stereo word doesn't fit into this, only regio word. So regio, it is non-regio selective because 50-50, one should have an edge over the other, should have a preponderance over the other. That is not happening. So it is regio, nothing to do with stereo, non-regio selective. It's not selective. What about this? This alcohol, when dehydrated by concentrated sulfuric acid water, you are getting 60% of this. 20% of this alkene and 20% of this alkene. So there are three alkenes. This is the major product. Tell me what name you will be given. Undoubtedly, since they are all structural isomers, this is regioselective because the products are in varying yields. So let's see. Cis-butene with bromine addition gives meso compound. Sorry, this is trans. I am so sorry. Trans-butene anti-bromine addition will give you meso product, and cis-butene will give you diol pair because of the same anti-bromine addition. So what will be the nature of this reaction? This and this together, they are stereospecific. Each one is a stereospecific reaction. If this gives this, its other diastereoisomer will give the other one, the racemic mixture, stereospecific. What about butan-2-ol with bromine? I'm sorry, concentrated sulfuric acid and heat will give you cis-butene 20%, trans-butene 60%. I have not shown but1 because that is a regioisomer, because I wanted to give the two stereoisomers. So undoubtedly in different varying quantities. So the name should be stereoselective, because these are stereoisomers, cis and trans, and varying amounts. One is major, the other one is minor. So it is stereoselective. With this, I conclude this program, and I'm happy to tell you that we have discussed a very important, fascinating aspect. I don't know how far you enjoyed my two videos on the selectivity and specificity. Please give me your feedback so that I will be more and more encouraged to, and you also try to interact with me over my email. I have been telling to my email. It is Sudhanshu trips @gmail.com. You can contact me if you have got any particularly if I have done any error here by slip of my tongue or slip of my pen, you point out. Bye bye.